Hello, my name is Jonathan Goldstein, and this is the video abstract for Ambrosia. First, everything you're about to see is real. Ambrosia is available on GitHub, and the project is ongoing with more releases coming out. It's used internally at Microsoft, and to give you an idea of what it does, it solves the following grand challenge. This is today with the code we have checked in. Ambrosia applications can seamlessly recover from a Windows VM running in the cloud to an ARM CPU running Linux at the edge without any loss of state and automatically healing connections to other applications, even though the developer doesn't have any calls to storage or network retries or reconnects. So in order to understand the challenge associated with that, let's consider a simple program that consists of two classes, a client class and a server class. The server class has a single variable called x, which is an integer, and one method called getIncInt, which increments that integer and returns it. The client class creates one of these server classes and then calls the method 3 times, writing the output to the console each time. What happens when we distribute this in the obvious way and put server class on one machine and client class on another? Let's suppose server class dies and we naively restart it somewhere in the middle of program execution. What are the things that can go wrong? First of all, we lose the state of the counter. So if getIncInt was called a couple of times and server class goes down and comes back up, rather than recovering the state of the counter at the time of the loss, we actually reset the counter to the initial value and client class will then output the incorrect thing. Also, the TCP connection itself has to somehow be healed. Finally, what if we were in the middle of an RPC call and server class went down? Client class could be waiting for the return value of the RPC call, and server class will never give it, and it will wait forever. So in practice, in order to solve this problem with cloud services, they journal all of the interactions between each of the distributed components and store it in durable storage before they act on it. Then your stateless function upon invocation typically goes out and gets some kind of current state and then journals all of the output to these durable queues before they're in turn acted on. Now, since the function invocations can fail halfway through, the application needs to establish a sequence number of all of the messages that travel between the two distributed components so that when things are partially executed and then executed again, the stateless function can then pick up where it left off. In addition, it has to carefully save state, for instance, here and here, during the invocation to make sure that things are left in a consistent state. It took me about a day to write this very simple function, and I'm still not 100% sure it's correct. This is very difficult code to get right. Now, those of you who are familiar with MapReduce and Spark know that your code doesn't look like this. In fact, it's much easier to understand. Why is that? That's because systems like these have a feature which we call virtual resiliency, inspired by virtual memory, which enables developers to run failure-oblivious code in a failure-resilient manner. So this works great for jobs, but what about other kinds of code and applications? What about services which never end? What about client applications that contain things like non-determinism and need to migrate across platforms? Well, in order to do these things, let's bring an old idea to bear. So let's first consider deterministic logic and then relax that. What can we do? Well, we can take all of the interactions and we can log them. So any incoming requests to this service code, we can make a log out of them, which we can then use to replay as long as the logic is deterministic in order to recover the state and the outgoing requests. So once we can replay in this fashion, you can ensure exactly once delivery of messages by automatically maintaining those sequence numbers, which I alluded to in the previous slide. So having a log is great. Look at all the cool things we can do. We can recover, which I already showed you. You can also use active standbys to guarantee high availability. These active standbys are consuming the log in recovery mode until the primary goes down. When the primary goes down, one of those active standbys can be chosen, and since it's already fully recovered, it can become the primary very quickly. You also get free time travel debugging. If you have a bug in your code somewhere, you have a replay log that gives you a repro for the bug, and you can test any fix that you have by running it against the replay log to see if the problem occurs again. So why isn't everybody doing this already? Well, first of all, everything that I told you works in a system that's deterministic. What about non-determinism? Applications have all kinds of sources of non-determinism. For instance, get time of day to get timestamps. When we replay and we call get time of day again, we'll clearly get a different answer than the first time. Also, what about user input or input coming in over the network that isn't replayable? Also, performance. There's this logging going on that may not have been going on before if your application wasn't resilient. How much does this extra work cost? Finally, as I alluded to, we want to be able to migrate across platforms and operating systems. So what do we do to enable us to do that, which on the client, when we're going from a Windows machine to a cell phone, is important? Well, what we're going to do is we're going to focus in on the performance angle. All three of those problems are addressed in the paper. But for now, I want to convince you that performance-wise, this is a very reasonable thing to do. In the top graph, we see the price performance of processing a message between two distributed applications where one distributed application just sends the other a byte array, and we vary the size of the byte array. The orange line is A.M.B.R.O.S.I.A, which is in C# or C# client. The blue line is gRPC. Now it's worth saying that A.M.B.R.O.S.I.A has all of these protections and consistency and all of that I've told you about. gRPC is just a straight up RPC framework without any kind of resilience whatsoever. Due to the quality of our implementation, which we describe in detail in the paper, we actually beat gRPC, which in a way we shouldn't, for small message sizes. And when we get to the large message sizes, we get network bound, and gRPC beats us by a factor of 2. This makes sense when you consider that all of the input that's coming in essentially needs to get sprayed back out so that it can get stored in replicated storage in the log, therefore having our effective network throughput. The top two lines are the top two cloud providers with an implementation using stateless functions similar to what I showed you earlier, and they are about 1,000 times more expensive per message processed. The bottom table shows A.M.B.R.O.S.I.A latency with respect to gRPC and a stateless framework. And you can see that the median for A.M.B.R.O.S.I.A C# is more than gRPC, but much less than what people expect today when they use stateless functions. And actually, we are the best 3 nines out. We're better even than gRPC, which doesn't do any kind of round trip to storage for durability. So how did we pull this off? How is this possible? First, consider that the cost of transferring and storing bytes is going down rapidly. We see our networks getting faster very quickly. We see bandwidth from storage going up quickly. But the cost of processing those bytes is actually improving very slowly. CPUs are not much faster than they were 10 years ago. So we looked into this and put numbers to all of this. So as of a year ago, we looked back 7 years. And it turned out that during that period, network and storage throughput price performance both improved by about 10 and 7 respectively, while CPU price performance only improved by about a factor of 1.5. So that means that strategies like A.M.B.R.O.S.I.A, which don't really increase the amount of CPU that you do by much, are actually pretty cheap. Furthermore, the future with terabit networking and NVRAM persistent memory looks to hold more of the same kind of thing. Networks are going to get faster without NICs becoming more expensive. You know, NVRAM in terms of price performance for bandwidth is already much cheaper than flash. So if you want to find out more, we have both this paper, which is what this talk is about, and also our GitHub repo on A.M.B.R.O.S.I.A. Thank you for your interest, and I'm looking forward to your questions.